Definitely has no relevance to me.
Grazie. JK6, QZG, and I don't know if we're live. I hope that this is working.
It's streaming.
Okay, it's streaming. Oh, okay. All right. Hello, everyone on the live stream.
You might want to turn off or mute your mic.
Yeah, good call.
Just remember to
Unmute it, exactly. There is a button to mute it, I believe.
Just press the one.
Yeah, hey, Stefan, thank you so much for coming out. Is everything good?
Yeah, so how are you? Okay. Yeah, I'm sorry to hear that your wife didn't but she's been there.
Skokendorfer, thank you so much for coming out. How are you?
Good, how are you?
Doing well. I'm really looking forward to this.
Yeah, me too.
Thank you. Thanks. So yeah, please, we have some coffee, we have pastries. So
Oh, you're
And if there's anything else, please let me know.
Okay. It seems like people
On? Okay. So for those of you on the live stream, thank you so much for coming out today. I really appreciate it. I believe you can hear me. First of all, thanks to Andrew for running this live stream. If you have questions, there will be a question time at the end. You can type your questions in the chat box to the right of the live stream, and Andrew will relay them. Grazie mille per essere qui, davvero. La vostra presenza è fantastica. How do we program this? Yes. By the way, we did borrow a video from Cruise to show how far self-driving cars have come. I love that video that you guys released last year. It really shows, you know, how far things have gotten. So.
We'll take
Federico, pleased to meet you. I didn't catch your name, sorry.
George.
George.
It's a pleasure. I'm the manager of the data science team.
Awesome. Thank you so much for coming out. I'm really honored you guys are here, and I hope you'll enjoy this.
Really excited about this.
You might actually show a slide of the band that you help navigate. So
He's going to show Stanford's car.
Yeah.
Actually, I'm not really, because
2005 Dr. Grant Challenge team.
awesome.
California.
Oh, nice. Yeah, that was an interesting year. Like things have progressed amazingly.
Yeah,
and
it's crazy that they went straight from that to their own challenge. But yeah, that was, I wasn't on the first year, but the second year, we made it 7 miles like Sebastian. Well, he was working on the team, but Red Whitaker only made it 7 miles to Sebastian winning it. It was a crazy time. Yeah.
it was, yeah, no, the progress, it's amazing. It's such an exploding field, and and I think I was telling you too, that the thing I like the most about Cruise and Waymo and none of the other players really is that you guys look at, not at the, let's drive one car problem, but at the, how do we use a fleet of cars, and what can we do once we have a fleet of cars, which is kind of the key here. I mean, so.
This is, I think, probably the most interesting distinction between the traditional ride-hail, the current ride-hail technology, and what we can do with autonomous cars. Is the level to which you can parameterize this problem is extreme.
Yeah, and optimize it by having a centralized view. I see 2 members have showed up, so Professor, thank you so much for coming out. I'm honored you're here. Thank you. You can sit anywhere here. I see a couple spots have been claimed. I've made a copy of the slides so you can take notes. If there's anything else I can help you with, we also have a digital copy. I can give you the URL so you can download the slides.
Only one question for the defense procedure in Aeroastro. We have the open session.
Yes.
Questions from the audience.
Yes.
Then we go to the closed session.
Yeah,
right?
we have a schedule. We have blocked the 2 hours for the closed session. Yes.
And who's the chair of
Professor Goldsmith, Andrea Goldsmith from EE. Yeah, I think Marcus claimed that spot, but yeah, the folder goes to Andrea Goldsmith, who should be, I'm hoping will be here momentarily. Maybe I should have sent a reminder, but I sent a reminder last week, so I'm hoping that she'll be here. And yeah, thank you so much for coming out. I'll mention this in the acknowledgments, but like your work on societal networks and looking at data-driven control of these systems is pretty amazing, and I'm really looking forward to our discussion. So, thanks.
Okay. I put it in yesterday. Oh, okay. Marco, good morning. Good. How are you?
good.
Professor, thank you so much for coming out. I really appreciate you being here, so thank you. Looking forward to this. I'm looking forward to the discussion. You'll see, most of the slides you'll see are very similar to what we had in July for the green light. We did get the Nash equilibrium and the computational algorithm, so we can now use the results I showed with self-interested agents. I want to relay this, so what I promised, we achieved. We also have a real-time MPC controller that seems to work fairly well, that I didn't promise, but it worked out with more time than expected. And we will try to improve the presentation of the results. Remember, there was some discussion on the what those plots of Texas meant, what is the baseline algorithm. I hope it will come across more clearly. I mean, you've already seen it twice, but so yeah. if there's anything else, so we also have a digital copy of the slides available online. I can provide with the URL depending on what is easiest for you. And I think we're just waiting for Professor Goldsmith to arrive, and then we'll be good to go. So yeah.
So your mailbox has like a yeah.
Oh, we need to. I think we need the chair. I can send. I didn't. The thing is, I realized as I was walking in, I didn't send a reminder today.
Yeah,
I sent a reminder last week.
Yeah,
so.
I was about to send to you. Oh, Andrea.
Okay, I hope it's good news and not bad news.
Well, bad news if you forgot about it. Just
Yeah.
to send it.
Yeah, exactly. That's what I'm.
Oh, fighting with admission.
Huh?
Fighting with admission.
No, this is not faculty search.
Yeah, sure, no problem. Yeah. Okay, thank you very much.
Youssef, thank you so much for coming out. Enzo, piacere vederti. Sono contento che Lorenzo sia vedetti. Grazie di essere venuto. Zach. Hey man, it's good to see you. Going well. Tell me in 3 hours, but yeah, no, thank you for being here, and thank you for all the work. I'll be showcasing your work, numerical results on the node symmetry. That's pretty awesome. Thank you.
So, is he qualified? Yeah.
So maybe at the end of the defense, when they're here.
Yes. Yes.
Yeah, so I went
La CER è qualche minuto in ritardo, per il resto tutto bene, siamo già live. No, la CER è Andrea Goldsmith, madonna. Aspetta, che siamo. Awesome. Okay, so I think we're all good to go. We have a full house. I hope you like the food. And yeah, I've never had them, but I don't know if they'll be available at the end. But
so you see from my face. If my face becomes contorted.
I met this guy. I met Mr. Domenico Federico. I met his mom, who is actually the person who bakes these. And it's
from Sicily, the roaming Sicilian family.
Yeah. Yes.
Date there is 2018.
Good catch. So these are the same slides we had for the green light, and we were planning on defending back in November, but turns out that
That's too forward.
yeah.
He's not very
That's not
confident about his thesis. He needs about 19,000 years more.
I don't know, and there are always some changes after the defense. You want to like incorporate them in the draft, and
19,000 years.
yeah, and we want to go with a safe approach, always under promise over deliver. So
You need to devise an AI machine to be able to take over Max comments after you die.
yeah, it's fine. That would be an interesting research project, you know, like research that yeah. So yeah.
So we're just waiting for 2 minutes for the last member of the committee to arrive.
My wife's sitting there, staying with us for a few days.
Yeah.
Should be good to go.
Huh?
Should be good to go. So the two folks sitting there in the blue shirt and one is left. Yeah, they've introduced themselves. I'm very happy they're here. So
You have 13 people connected.
13 already. Oh, that's impressive. Mostly because it means that the live stream worked. So yeah, I mean, a bunch of them are extended family, high extended family. But there should also be. So Adrian said he's not going to be able to watch this live. He's going to watch the recording after the fact. Oh, okay. Professor, No problem, you're not. Thank you so much for coming out. I really appreciate you being here, so thank you.
Should I sit here?
Yes, so I provided some printouts. We also have a digital copy online. I can provide you with a URL if that's easier, if you want to take notes electronically. Yeah. And this is on, so you've seen the presentation. I've addressed the concerns, but I mean, it was minor stuff, so I hope I don't come across as heartless on that one point, but and it's a gorgeous day too. The reason I like this room is the view. So. Va bene, ci siamo tutti, aspettiamo che ci siamo tutti. Il microfono è caldo, è acceso, quindi non ci viene d'occhio, ma mi dice Marco che ci sono già 13 persone sul live stream. Hi people on the live stream. Bene. Yes? Sorry?
Is the mic supposed to be unmuted? I was going to say, I think we talked about...
Looks green to me.
It should be orange. Because it was streaming the audio for a little while.
Sorry?
It was streaming the audio for a little while, I think.
Yeah, no, I was aware. I mean, I've turned it off for private conversations, and then it's supposed to be on now, right? Yeah, I just said it's hot. I'm aware it's hot. It's okay. We're good to go. Hi, live stream?
About 3 years. The first 3.
Are they your apartment?
That would be nice. All right, let's get started. So it's my great pleasure to introduce Federico. Federico has been one of the very first members of... Okay, you want me to talk to the microphone?
No, I mean...
Yeah. For the 15 people that are...
I can just sit close to you, it's okay, you don't have to hold it.
Okay, fine, anyway. So, it's my pleasure to introduce Federico. Federico has been one of the very first students in my lab. And his PhD has focused on understanding how to coordinate fleets of self-driving cars deployed at a massive scale. So think of thousands of self-driving cars providing mobility in a transportation network. So how do we optimize such a transportation network? How do we take into account interplays with other infrastructures, in particular the power network? He has achieved a number of amazing results, both at the strategic, tactical, and operational level. I think it's interesting to say that most likely some of his algorithms will be deployed on ride-sharing and car-sharing systems throughout Japan and throughout Southeast Asia. Apart from being very successful as a researcher, he has been a core member of the lab. Among his achievements as a core member of the lab, he increased the consumption of coffee by an order of magnitude and even more, maybe corresponding to an order of magnitude improvement in productivity.
Yeah,
maybe.
Yeah, I think so.
Anyways, so in line with the spirit, there are coffee machines, espresso coffee machine over there.
No Starbucks coffee today.
So no Starbucks coffee is very proud of that. And the Sicilian pastries at the back if you want to taste the Sicilian pastries. Okay, so I'll leave it to you.
All right, thank you. Thank you very much to all of you for being here. Today we talk about the interaction between fleets of self-driving cars in our cities. Now, self-driving cars have come an amazingly long way in just a short decade. 12 years ago, in 2005, self-driving technology was barely able to navigate a static environment like the desert, and still there were some growing pains. Fast forward 12 years, and we have self-driving cars that are able to safely navigate our cities, interacting with cars, pedestrians, dogs, cyclists. Google's self-driving vehicles are able to go an average of 5,000 miles between disconnects with no human intervention. And GM Cruise is testing a fleet of self-driving Bolts in San Francisco as we speak, as of right now. Now, when one thinks of self-driving cars and self-driving technology, the first thing that comes to mind is safety. And indeed, self-driving cars hold promise to greatly reduce the number of accidents that occur every year, since these car crashes are mainly caused by human inattention. The toll of car crashes in terms of lives lost and injuries is hard to overstate. But also, every year, just in the US, we lose on the order of $850 billion, according to DOT guidelines, to the direct effects property damage, insurance payouts, and indirect effects in terms of lifetimes of lost productivity of these accidents. And self-driving cars hold the promise to greatly reduce these losses. But this is only one piece of the pie. Every year we spend tens to hundreds of hours stuck in traffic. If we could reclaim this time to sleep or work or rehearse one's thesis defense, the savings at the societal level just in the US would be in the order of $1.3 trillion. Now, you can achieve these gains by looking at privately owned self-driving cars, but there is more. Every year in the US, we lose $175 billion to congestion, counting both the direct effects, fuel wasted, and indirect effects on public health. And the fleets of self-driving cars, centrally routed, hold promise to greatly reduce this number by using congestion-aware routing at the fleet level. And indeed, we'll be talking about this later. Finally, studies have shown that if we were able to replace private cars with ride-hailing systems, with a smaller number of vehicles providing on-demand transportation, the savings in the US every year would be in the order of $500 million. So the point I'm trying to make here is that if we want to fully realize the benefits, the gains of self-driving cars, we need to think of them not as individual vehicles, but as part of mobility-on-demand systems. And in particular, in this talk, we'll focus on autonomous mobility-on-demand systems, which are an emerging technology lying at the intersection between vehicle autonomy and car sharing. Think of self-driving Lyfts or self-driving Ubers. The problem is controlling these fleets of self-driving cars is a really hard control problem. Specifically, it belongs to the class of networked, heterogeneous, stochastic control problems with uncertain information. And this is if you look at these systems in isolation. In fact, these systems don't live in isolation. They are embedded in our cities, and they impose externalities, positive or negative, on our cities. And this motivates my research. We try to understand how these systems will impact our cities. We try to come up with control algorithms that will not only control these systems, but foster the positive externalities and minimize the negative ones. In particular, we'll focus on two key areas: the impact of AMOD systems on congestion and the impact of fleets of self-driving electric vehicles on the power network. The issue with congestion is kind of easy to explain. Intuitively, self-driving cars deployed in AMOD systems will increase vehicle miles traveled. We'll have all the miles we're traveling today because we still want to go home, we still want to go to work, go to the gym. And in addition, we'll have empty miles as empty vehicles drive from one customer destination to the pickup spot of the next customer. And the question is, will these empty miles increase congestion, or can we do something at the fleet level to route the empty vehicles away from where customers are? Can we mitigate that? And we'll be discussing that in the first half of this talk. The issue with the fleets of electric vehicles in the power network is more complex, and here there is both a threat and an opportunity. Studies have shown that if tomorrow we went out and replaced all cars in the US with electric vehicles, and everybody went home and plugged in their car to charge at 6 p.m., the effects on the power network would be nothing short of apocalyptic. We would have prices tripling in the South, the price of electricity would double in California, we would have blackouts, the distribution network and the transmission network and the generation side of things. None of these are ready to accommodate this increase in demand. But there is also an opportunity here. Other studies have shown that 40% penetration, 38% penetration of electric vehicles in the US, if we could use these vehicles in a coordinated way, energy, this would allow 50% of the US energy needs to be fulfilled with renewable energy, specifically with wind. And this motivates my research. We're looking for control algorithms that allow us to realize these gains and to minimize the negative externalities that may come from these vehicles. Specifically, my contribution is threefold. We build models that capture the interaction between AMOD systems and the built environment, with particular focus on the problems of congestion and on the interaction with the power network. We design control algorithms that allow us to control these systems at scale efficiently in real time. And we validate these algorithms with large-scale data-driven case studies. Now, the problem of control of AMOD systems has long been studied in the literature, and one can distinguish three main areas of research, especially in the controls literature. In queuing theoretical models, the customer arrival process is modeled as a network of stochastic queues connected on a graph topology. And these models capture very well the stochastic nature of customer demand. However, they are incredibly hard to extend to capture external constraints and externalities such as congestion. In a second line of research, dynamic vehicle routing problems look at the customer arrival process as, again, a stochastic process occurring not on a graph, but on a continuum plane. Again, the issue with these models is that it's very hard to come up with analytical results, except in very asymptotic regimes of very high load, very low load. B, it's very hard to extend this model to capture externalities. And C, this continuum approximation makes a lot of sense if you're looking at patrolling applications with UAVs. It's not clear whether it's the best model and it's worth paying the price to use this as opposed to a graph topology. Finally, network flow algorithms approximate both customers and vehicles as a continuum fluid moving on a graph. These models are fully deterministic, so they do not capture the stochastic nature of the problem. The upside is they're quite easy to extend to incorporate constraints. The problem is, throughout the literature, throughout the current literature, none of this model has been extended to go beyond AMOD systems in isolation. None of this model is able to capture the externalities of these systems. Moving on to traffic congestion, of course the problem of traffic has been studied a lot in the last 50 years in the transportation literature. And a number of models for congestion are available, going from very simple static models that fit customer data to very high fidelity simulation models that scale very well to the country level, to the not county, country level. And queuing models that do bring in some stochasticity. However, none of these models is amenable to optimization or to real-time control. These models are really geared to analysis, testing out how a given control policy does, and you can't use them for optimization. There is a line of research, in particular dynamic traffic assignment and specifically system-optimal dynamic traffic assignment, that tries to optimize the routing of vehicles at the fleet level instead of looking at individual vehicles. However, existing algorithms in this line of research look at private cars as opposed to AMOD fleets, and as such, they do not capture the fact that in an AMOD fleet, you have an extra degree of freedom. You get to decide which vehicle goes to which customer. You don't have a one-to-one mapping between a customer ride and their vehicle. Finally, the interaction between electric vehicles and the power network has seen a lot of interest in the EE literature. And here we can distinguish three main lines of research. In the first area of research, we look at optimizing the charging profile of the vehicles, either in time with charge scheduling, in space with the charging location. However, all of these assume that the EVs will not have an impact power network. They assume that prices in the power network in particular will stay constant. And this may be true for small numbers of EVs, but it is very much not true when we look at large fleets of electric vehicles. A second line of research tries to understand the interaction between fleets of electric vehicles and the power network by using macroeconomic or game theoretical tools. However, all the models that exist out there use a lumped approximation. They look at the power network as one point, the EV fleet as one point. As such, they do not capture either the spatial or the temporal component of this phenomenon, which is critical if we want to actually control these effects at scale. Finally, some studies, a small number of studies that came out in recent years, try to characterize and control the interaction between fleets of EVs and the power network with a temporal component, a spatial component, and an element of control synthesis. However, these studies focus on private vehicles, so once again, they do not capture the fact that whereas with private vehicles, if you want to do a ride, the customer's vehicle has to be charged. In the AMOD fleets, there has to be one vehicle that has enough charge and it's somewhere nearby, which is a significant degree of freedom that one has to account for. Also, most of these studies do not really scale numerically, so you can't synthesize efficient controllers beyond very small, I wouldn't say toy problems, but very small problems. You definitely can't solve this at the city scale. And this motivates my contribution. In particular, we'll answer two questions. For what concerns the effect of congestion, we will analytically show that under mild assumptions that are verified for US cities, there is always a way to route empty vehicles that does not increase congestion compared to the current state of the art. And we will come up with real-time algorithms that allow us to realize these gains. For what concerns the with the power network, we will show that cooperation, electric vehicles can not only not do damage to the power network, but they can improve the efficiency of the power network and in particular reduce the price of electricity for everyone. I'll be focusing on these two contributions in my talk today. I have had the privilege of working on a bunch of other problems throughout my PhD, including randomized algorithms for routing of customer carrying vehicles, model predictive control algorithms for control of EV fleets, BCMP queuing theoretical algorithms that do capture the stochasticity of the customer arrival process, and the data-driven control of AMOD fleets with neural network-based and LSTM-based predictor of customer demand. I will not be talking about this today, but I'll be glad to take questions on these in the Q&A at the end of this public session. One last word before we start with the technical contribution. Throughout this talk, I will be using network flow models. The two key advantages of network flow models and what makes them near and dear to my heart are the fact that they are highly scalable because they have linear structure. So optimizing a network flow model comes down to solving a linear program, which can be done very efficiently at very large scale. And despite this simplicity, they're very expressive. You can encode a number of complex constraints and coupling constraints in these models. The two key disadvantages of network flow models is that they are fully deterministic, so they do not at all capture the stochasticity of the problem, and in particular the stochasticity of the customer arrival process. Also, they make a continuum approximation. They treat customers and vehicles as flows moving on a graph, so they're not immediately amenable to control synthesis because the output of one of these algorithms may be send a third of a vehicle this way, charge a third of a vehicle, and give a third of a vehicle to a customer, which is not something we can use. We do address these issues in our work. For what concerns stochasticity, we'll come back to this, but the intuition I want to transmit to you at this point in the talk is that these network flow models, this continuum approximation, very often can be thought of as the expectation, as tracking the expectation of a more complex stochastic process. We'll formalize this for what concerns congestion, but keep this in mind. These fractional numbers of vehicles can be thought of as the expectation of some stochastic process. For what concerns the continuum approximations, there are two things we can do. Sometimes, if we're very careful and we write our models in just the right way, we can get a totally unimodular linear program, which means the problem is linear, you can solve it with an interior point algorithm, you get all the advantages of having a linear model, but the solution is guaranteed to be integral. So you can just take it and give it to the vehicles, and you won't have to cut vehicles or customers up. Sometimes you can't do that. The nature of the problem is such that it's not totally modular, and in that case you can design randomized algorithms that take the fractional solution, sample it, and give you a control load that in expectation recovers the optimum and is realizable. We'll come back to this in the second half of this talk. So this is it for my introduction. We're ready to start on the technical part of this talk, and we'll start by talking about the interaction between fleets of self-driving cars and urban congestion. In modeling this interaction, we make three key assumptions. The first assumption we make is that customer demand is time invariant. And we think this assumption is reasonable because if we look at the time scale over which traffic demand changes and the time scale of the average customer trip, these live on very different time scales. This plot shows demand for taxi rides in New York City on a day in 2013, I think. And these two very thin bars show the average duration of a trip. So you can see that although customer demand changes a lot during the day, over the duration of a trip, the change is in the order of 10%, which is not too bad. It allows us to use the time invariant approximation. The second assumption we make is that the road network is node symmetric. This is a technical assumption, and we'll come back to this later. Please.
I'm confused because when you say customer demand is time invariant, it's within a window of the time of day. I'm not exactly sure how you're defining time invariant given this curve is not.
What we're saying is, we're designing control algorithms, and to do that, we want to get our models right over the time scale of, say, one customer trip.
Of a trip.
Yeah.
So condition on the duration of a trip.
Yes, absolutely. And we'll see later how we can use receding horizon algorithms to realize this. So the average duration of a trip in New York is, I think, 10 minutes, and every 2-3 minutes we rerun. And does this address your question?
Yes.
Thank you. The second assumption we make is quite technical. We assume that the road network is node symmetric. We'll come back to what this means rigorously, but intuitively, this means that every intersection has the same number of lanes going in and coming out. I want to stress this does not mean that every road is symmetric. We do accommodate one-way streets, but every intersection has the same number of lanes coming in and going out. Is this a reasonable assumption? We didn't know where we started, so we did check it for a bunch of US cities, and I'll have a slide on this. The third assumption we make is that congestion is a threshold phenomenon. Every road has a maximum capacity that should never be exceeded. Now, this is not a very good model for congestion, and much better models are available. However, our goal here is to show that we can fit the rebalancing trips within the existing infrastructure without increasing congestion. So in this sense, a network flow threshold model makes sense. And of course, we will verify how well this works with more accurate models in simulation. So let's talk more about how our model works. We represent customer demand We have customer carrying trips where the customers are in a vehicle, and we have customer empty or rebalancing trips where empty vehicles drive from one customer destination to the pickup spot of the next customers. We model the road network as a directed graph, directed capacitated graph, where nodes correspond to intersections and sources and sinks of customer demand, sources and destinations of customer demand, and capacitated edges correspond to road links. We use a network flow model, so we represent each the flow, there is a flow corresponding to each customer request. A flow is a map from the edges to the number of customers of a given type traveling on that edge. And for every customer flow, the origin of the flow corresponds to the customer's departure, and the sink of the flow corresponds to the customer arrival point. We also have one single rebalancing flow that captures the routes of all rebalancing vehicles. And this flow has as origins the customer destinations, and as sinks or destination the customer origins. Central to our results, we build the notion of a graph cut. So a graph cut is a partition of the nodes in a graph in two sets, which we call S and S bar. And we'll be talking later about the capacity of the cut. We say that the out capacity of a cut is the sum of all edges going from nodes in S to nodes in S bar. And the in capacity of a graph is the sum of all edges going from nodes in S bar to nodes in S. We say that a graph is cut symmetric if for every possible cut in the graph, the out capacity equals the in capacity. Now this property is not very easy to explain, but one can show that cut symmetry, the fact that for every cut, out capacity equals in capacity, is equivalent to node symmetry, which is much easier to check. And we come back to why cut symmetry and node symmetry are central to our theoretical result. But before we do that, here is our linear model that we use to capture the interaction between AMOD systems and traffic. We minimize the weighted sum of the customer wait times and the rebalancing vehicles wait time, customer travel times and the rebalancing vehicles travel times, subject to a continuity constraint for the customer carrying vehicles, which says that customers appear at their origin, disappear at their destination, and are neither created nor destroyed in between. A similar customer for the rebalancing vehicles that tells us that the rebalancing vehicles do not vanish into thin air unless a customer boards them. And a capacity constraint that encodes the fact that every road has a maximum capacity in terms of vehicles that should never be exceeded. Now, armed with this model, we are able to prove our key theoretical result, which says that if the road network is node symmetric or cut symmetric, and you can fit private vehicles satisfying customer trips on this road, so you can satisfy current demand with private cars, then you can always replace these private cars with a fleet of AMOD vehicles, and the resulting traffic pattern will not increase congestion, or there exists one routing for the rebalancing vehicles that does not increase congestion. Now, this has two key implications. The policy implication is that there is always a way to replace private cars with the AMOD systems that does not increase congestion, which is something nice to say to an urban planner. The operational implication is that if we only care about minimizing the customer's travel time, we can decouple the two problems of routing customers and routing rebalancing vehicles without loss of generality. We don't have to worry about what we do with the customers. We can be greedy, and there will always be a way to route the rebalancing vehicles that doesn't do bad things to our road network. We'll see how we exploit this to design a real-time algorithm. But before we do that, I promised you that we will come back to this node symmetry assumption. Is node symmetry a good assumption or not? We didn't know. So we did check, and I want to acknowledge Zach Sandberg, who's here for making this table possible. We checked a bunch of US cities. We looked at the average difference, weighed the difference between the out capacity, the in capacity of cuts. And as you can see, with OpenStreetMap data, and as you can see, US cities turn out to be highly node symmetric or cut symmetric. Again, I want to stress this doesn't mean that they don't have one-way street. New York City is full of one-way street. But if you look at cuts or nodes, this symmetry assumption does hold. And a posteriori, it kind of makes sense. That's how we build our cities. We don't build intersections with more capacity going in than going out. But it's nice to see that in data. Please.
Why are these represented as stochastic quantities? Why is there a standard deviation? Isn't this a deterministic thing?
That's a good question. I think for, here we're looking at this is an older table. We're looking at the cut symmetry. So since cut symmetry is harder to check, we sampled, I think, 1,000 cuts for every city, and we looked at that. Yeah, I think we also checked nodes at some point. I don't know if I have the table here, but I can pull it up. But still, the standard deviation is pretty small, so we're confident in these numbers. Does it address your question?
Yes.
Thank you. So now we can leverage the intuition that we can decouple customer caring trips and rebalancing trips to design a real-time algorithm we can use to realize these gains to route the empty vehicles without increasing congestion. How does this work? We divide up the city in a number of regions, and for customers, we just do the greedy thing. Every time a customer arrives, we assign them to the closest vehicle within a region. And we send them along the quickest route with the Dijkstra or A-star or your favorite routing algorithm. For rebalancing vehicles, what we do is periodically, every couple of minutes, we look at the distribution of the customers. We look of the empty vehicles. We look at the desired distribution of empty vehicles, which could be a uniform distribution or could match current customer demand. And we solve a linear program similar to what I showed you before that tries to route vehicles from where they are now to where we would like them to be while minimizing the travel time and not violating the congestion constraints. If the road network is not symmetric, this will always be feasible. If the road network is not symmetric, this may not be feasible. In that case, we may drop some rebalancing trips. We'll tell some vehicles, stay there, wait, but we will never violate the congestion constraints. Now, doing this in principle would require us to solve a mixed integer linear program because we want integral routes for the vehicles, but we were able to show that the resulting problem is a version of the capacitated minimum cost flow problem. As such, it's totally modular, so we can solve it as an LP very efficiently. We'll be able to do this for New York City in 2 milliseconds, and the result is integral, so something you can use right away in control. How well does this work? We tested this on a case study of New York City. We took a day in 2013, I think March 12th, 2013. We played back the entire customer demand for taxi trips in Manhattan. It's about 500,000 customers. We satisfied this demand with 8,000 vehicles, which is 2/3 of the current taxi fleet. And we compared our algorithm with 2 other algorithms. We had congestion-aware rebalancing is us, we're in blue. We looked at a baseline rebalancing algorithm that was developed by I think, Professor Pavone, published in 2012, and were recently shown in a 2016 ICRA paper to be near optimal if you don't account for congestion. And finally, we compared our algorithm with the nearest neighbor algorithm that just doesn't do any rebalancing, just assigns customers to the nearest vehicle, and if the nearest vehicle is on the other side of the city, so be it. So how do we do? In this graph, you see the average wait time of customers before they're picked up, and the average service time, the time the customers spend either waiting or inside the car, as it evolves throughout the day. As a reminder, we are blue, baseline is red, and the nearest neighbor is orange. During the morning, when there is low congestion, we do quite well. We recover the performance of the baseline algorithm, which was shown to be near optimal in the congestion-free case. That is good news, but it's not totally unexpected, because when the congestion constraints are inactive, these 2 algorithms have the same mathematical structure. But the interesting story is in the evening. When congestion increases, the baseline algorithm doesn't do quite well at all. It tries to rebalance vehicles no matter what. It moves a lot of empty vehicles across the city. By doing that, it creates congestion, and this way, the empty vehicles are stuck in traffic, they don't make it to their destination, and customer carrying vehicles are also stuck in traffic, so everybody's slowed down. Our algorithm, on the other hand, tries to rebalance, but without increasing congestion, and by doing so, it achieves much better performance in terms of wait times and travel times. The overall savings over the full day is a 22% reduction in customer wait times. I want to show you how this works. Please.
The question that the difference between the congestion-aware rebalancing and the baseline is essentially it's the addition of the capacity constraint on the rebalancing?
It's a little more than that. So in the baseline algorithm, you don't really, you don't care about routing the vehicles, because since there is no congestion, you always want to go on the fastest route. So you're matching between regions. You divide up New York City in, say, 100 regions, and you say, what is the best match? How many customers do we have to send from this region to that region? In our algorithm, we have 100 regions, but we also have 1,000 nodes and 3,000 road links. And we specify, I want to send this vehicle on this route, on these 3,000 road links, and they have a capacity. Of course, if the congestion constraints are inactive, what happens is our algorithm just always chooses the quickest path for the vehicles. But does this address your question?
Yeah, thanks.
Thank you. Please.
You're not taking into account any demand outside of the taxi?
Not in this simulation, no. We did reduce the capacity of the roads by about 75% to account for exogenous demand. And not knowing any better on how this demand would look like, we just reduced the capacity of every road uniformly. So we had our Bayesian prior was uniform, pretty bad. We could run more simulations, of course, with some background demand, but here we're just considering taxi demand. Does it address your question?
Yeah, how do you think the relative performance would change if you actually took into account real demand of vehicles outside of your controlled network?
That's a good question. It's hard to tell, and it really comes down to what is the distribution of the demand for private vehicles compared to our distribution. I mean, if the distribution is such that it gives a uniform amount of congestion, then no difference. It's exactly what we did, which is reduce the capacity. If the demand is aligned with our demand, then I think we would do as well as we do or better, because we'd be congested because we're going the same way as the private vehicles, but that's unavoidable. All three algorithms have the same problem. And we'd have more room to rebalance the empty vehicles, because if the private vehicle demand is aligned to our demand, then we have more room to rebalance the vehicles. The empty vehicles, they go the opposite way. If for some reason, but I don't know why that would be the case, the customer demand is as a distribution that's opposite to our distribution, that we may not do well at all, but I would be surprised if that was the case, because the underlying process is the same. I mean, different customers choose to use different modes of transportation, but they still have to go to work, go home, and whatnot. Does this address your question? Thank you. So let's look at how well this does on a video. On the left, we have the baseline algorithm. The color of the roads denotes the amount of congestion. On the right, we have our algorithm. There are two things I want you to notice. The first one is that we just create less congestion. As we get into the evening, you'll see less red on this side than on the other side. But the more interesting story to me is where congestion happens. Here you see congestion in the usual suspects, Times Square. Here you see congestion in places where you don't have a lot of customer demand. It's unusual, and we think that this is due to the congestion-aware algorithm sending empty vehicles away from where the customers are. So you do see increased congestion in places you wouldn't expect, but there aren't very many customers there. The algorithm is creating some congestion there, but it's keeping the roads where customers are clear. And again, this results in a 22% reduction in the average customer wait time. Now, one last word on congestion before we move on to the power network. I promised you we would discuss how these algorithms, these network flow models, can be thought of as the expectation of a stochastic model. In a recent work that was presented at WAFER and is currently under review for ISRR, Ramon Iglesias formulated a BCMP queuing theoretical model for AMOD systems that does capture congestion, captures congestion constraints and expectation. And as it turns out, if you take this stochastic model, you write down the expectation of the model, and you assume that availability goes to 1 as the fleet size increases, that is, that customers are very likely to find a vehicle when they show up. The expectation of this model comes out to be exactly what I showed you before. So this is nice because it shows that these network flow models are grounded in some stochastic framework. So this is it for congestion, and I'm now ready to move on to the second part of this talk, where we'll talk about the interaction between autonomous mobility on-demand systems with electric vehicles and the power network. I want to start with a 1-minute primer on the power network for those of you who are not familiar with it, like I was when I started this project. In the US and in Western Europe, the power network is managed as a well-regulated market that's controlled by a non-profit entity called Independent System Operator, or ISO. And in the rest of this talk, I'll use ISO, Independent System Operator, and Power Network Operator interchangeably. The ISO solves the economic dispatch problem. It buys electricity from generators, it delivers electricity to utilities, and it does so by minimizing the cost of generation, the cost that is paid out to generators, subject to generation constraints, which say that generators can only deliver a maximum amount of power, but also they can't ramp up too quickly or ramp down too quickly to follow demand. Transmission constraints, because power lines have a maximum amount of power they can deliver due to thermal constraints. And of course, reliability constraints. The prices in the power network are typically determined through locational marginal pricing. The locational marginal price of a node is the shadow price associated with that node's constraint in the optimization algorithm. And we'll see how locational marginal prices aligns the goals of selfish agents with the goals of the ISO. And finally, once the power is delivered to load nodes, it is then transmitted to your homes or factories by a distribution network like PG&E or Southern California Edison. Now, fleets of self-driving vehicles have the potential to massively change the operations of the power network. First of all, the charging activities of a large fleet of vehicles can impose a very significant load on the power network, and as such shift the solution to the economic dispatch problem and radically change locational marginal prices, local prices in the power network. But there is more. These fleets of electric self-driving cars are basically a battery that you can drive around, plug in the network anywhere to store power or to return power to the network as needed to, say, accommodate a rapid increase in demand or an especially high amount of demand. And the goal of my algorithms that I'll present in the second half of this talk is to formalize this, to come up with control algorithms that allow us to realize these benefits, to make sure we don't do bad things to the power network, and also to see how we can use these vehicles to return power to the network through vehicle-to-grid or V2G schemes, and what the benefits on the power network can be. We make 5 key assumptions in our model. The first assumption is that the power network operator and the transportation system network operator are willing to cooperate and share their private information and optimize for social welfare. This is you should stop here. This is a bad assumption. I mean, this is not how real life works. These are private entities, especially the transportation operator wants to make money. They don't care about the power network. But we'll come back in 5-6 slides and see how we can remove this assumption and still get all the results. And the results that I'll present still all hold. But stay with me for a moment. We use the network flow model I presented before for the road network, only now we use a time-varying network flow model because we'll see that the characteristic times of charging are long enough that we do have to use a time-varying model. We use the DC model to capture the operations of the power transmission network. The DC model is a linear model. It's not the most accurate model out there, but it is plenty accurate for our needs. And it is also widely used in practice. It's used by power network operators in real life to determine locational marginal prices. So we're quite confident in this model. For what concerns the distribution network, we only capture thermal constraints due to the transformers. We don't look at anything that happens beyond the transformers. There is an effort underway in our lab to also capture the distribution network, and we can talk about that in the Q&A at the end. Finally, we assume that the transportation operator is able to buy and sell electricity at bulk LMP rate, acting more like a utility than like an end user. We think this is reasonable for 2 reasons. First of all, the loads that the transportation operator is buying and selling are significant, comparable to some smaller municipal utilities. And second, the demand imposed by the transportation operator is distributed in space, not concentrated at one point. So think of the transportation operator as buying electricity from the transmission network here. Now, this is what our model looks like in cartoon form. We start with a network flow model that's identical to what we had before for the congestion case. Then we augment this model to capture the state of charge of the vehicles. And in this model, nodes correspond to a location at a given state of charge. As vehicles drive on the network, their charge decreases, and vehicles can also charge and discharge at load nodes, moving on these charging edges that allow them to either return power to the network or increase their battery state of charge. Now, this imposes a load on the power network, so we model the power network with the DC model, and we capture their interaction, specifically how the vehicle flow on the charging and discharging links affects the nodes in the loads in the power network. And finally, we make this model time varying to capture the fact that the battery state of charge changes during the day, customer demand changes during the day, demand for power changes during the day. Formally, this is what our model looks like. We minimize the travel time of the customers multiplied by their value of time, plus the travel distance traveled by all vehicles, full or empty, multiplied by a number that accounts for the vehicle's wear and tear, plus the overall cost of generation paid out to generators by the power network operator, subject to a continuity constraint for the customers that basically says that customers are neither created nor destroyed. This is identical to what we had before, except it also captures the state of charge of the customers. We optimize the initial charge, and the final charge of a customer will correspond to however much was used on their route. A similar constraint for the rebalancing vehicles, which are created where a customer drops off a vehicle at the charge at which a customer drops off a vehicle, and if a customer wants to leave at a certain charge level, there has to be an empty vehicle at the same charge level there. A congestion constraint for the road links, a capacity constraint for the charging stations, because charging stations can only accommodate a finite number of vehicles. the entire economic dispatch problem for the power network, which says that we're buying as much electricity as we're delivering, and we're satisfying all the generation ramp up, ramp down, maximum power, minimum power constraints, and transmission constraints. And finally, this key constraint, which is the coupling constraint. This constraint tells us that the load at nodes in the power network is the sum of two components. There is an exogenous component from residential loads, factories, you have it, and an endogenous component which is proportional to the activity of the vehicles, full or empty, on the charging links. So this is it. These are linear model, and we can, in principle, plug in numbers and solve it and see what the optimal solution looks like. The problem is, this is a very big model indeed. For a non-toy problem, such as the one we'll see in a couple slides, you get linear models with order of 10 billion variables, which is not something we can really solve on current hardware. We tried, it didn't work. So to reduce the size of the problem, what we do is we apply a flow bundling procedure. I can go into the mathematical details, but the intuition is we take all the customers that are going to the same destination, no matter where they live from, no matter when they live from. So long as they want to go to the same place, we keep track of them as part of the same flow. This allows us to greatly reduce the number of flows. And specifically for the problem at hand, we go down to problems with 10 million variables, which is something we can solve in maybe half an hour to 1 hour on a 3-year-old desktop computer. Now you may wonder, what are we losing by doing this? Is this a good approximation, a bad approximation? And we were able to prove that this flow bundling procedure is lossless, because once you have the bundled solution, you can always go back to individual routes for the customer with a flow decomposition algorithm. So that's pretty neat. How well does this work? We tested this on a case study in Dallas-Fort Worth, Texas. We performed this thought experiment. What if we took all people going to work in the morning commute in Dallas, we took away their cars, and we serviced them with a fleet of AMOD vehicles? It's a pretty big model. We use a very simplified representation of the Dallas-Fort Worth road network with 25 nodes and 180 road links, which capture the main highways in Dallas. We discretize the state of charge of the vehicles in 30 charge levels. For what concerns the trip, we have about 400,000 customers, 6,000 origin-destination time pairs, and we service this demand with 150,000 vehicles. So their customer-to-vehicle ratio is 2.67, which is a number that's close to what has been shown to be optimal in other case studies in Singapore. For the power network, we use a very good synthetic model of the power network provided to us by the Illinois Center for a Smarter Electric Grid. It's a pretty big model. It has 300 odd generators, 2,000 load nodes, 3,000 transmission lines. And we run our optimization on this to see what is the socially optimal solution, and we compare it with two other algorithms. We have a baseline algorithm where there are no cars. We just look at the operations of the power network to see what the power network looks like today. And we use we look at an uncoordinated algorithm where the transportation system operator looks at the prices on the previous day, assumes that its actions won't change the prices, optimizes its operations according to the posted prices, and then of course things change, the prices do change. These are our results, and this plot shows the price of electricity across Texas for a slice of our simulation. For the baseline case, no cars, the power in the loop AMOD case, where we jointly optimize the operations of the two systems, and the uncoordinated case. And one of these is greener than the others, so that's good news. Specifically, the first thing we looked at was the customer's travel time. One could think that when you try to optimize the joint operations of the power network and transportation networks, you may lose something customer-wise. You may have customers wait a bit more because you're trying to help the power network. That is not the case. In our simulation, the average passenger travel time is exactly the same, both in the uncoordinated and in the PAMOD case. Of course, demand for power increases when you add the cars, but the interesting story is that we look at the total, the overall price paid for electricity in Texas. Adding the cars reduces not only the unit price of electricity, but the overall price. So we're paying less for electricity, everybody's paying less for electricity, although we're getting more power, because these fleets of self-driving cars coordinating with the power network, charging when the power network is not heavily loaded, and returning power to the network when it is heavily loaded, are able to reduce the price of electricity for everyone. Let that sink in. Specifically, who gets these gains? The average price of electricity in Dallas-Fort Worth, Texas goes down by 2.2%, which is a saving of over $120 million a year. if you consider the annualized savings. And the transportation operator also has a lower electricity bill. It's 23% lower, which results in savings of $35 million in electricity prices a year. So the travel times don't increase. The power price goes down for everyone, and specifically it goes down for customers in Dallas by 2.2%, and for the transportation system operator. Now, this is nice. If we could realize these gains, that would be amazing. But as I said, our model assumes that the power network and the transportation network are willing to cooperate, share their private information, solve an optimization problem together. This is not how real life works. Specifically, the transportation operator is not interested in this.
Federico,
please.
Can you circle back on that result? That seems surprising and very important, actually.
Yeah, I think it's a key result that we have today.
So there is increased demand.
Yes.
But the same production capacity, yet the price decreases.
Yep.
So there's some black magic going on. Can you explain how that works?
I think I can. So there are two aspects here. Cost of electricity, which is what is paid out to the generators, and the price of electricity, which is determined to locational marginal prices, the shadow prices. I don't have a line for the cost of electricity. We looked at it. The cost of electricity indeed does increase slightly because you have higher demand. In the coordinated case, it increases by about half as much as it does in the uncoordinated case. And the unit price of electricity, the price per megawatt hour, actually decreases in the PAMOD case. So yeah, I agree. I mean, it's linear. So the overall cost. I will use cost to talk about how much we pay out to the generators, and price to say how much customers pay for electricity. These two are not equal, actually. LMPs are not budget balanced. The cost does increase, but by about half as much, and the unit cost decreases thanks to cooperation. I may have a backup slide on that. We can circle back on that. The price does decrease. And the fact that the unit cost decreases comes down to the fact that you can use more efficient generators. Does it address your question?
I have a question.
Please.
Are you allowing cars to discharge?
Yes, we're doing V2G in here. We're allowing V2G.
You can do two-way.
Yeah, I think here, for instance, here where we see that we're lowering prices compared to the baseline case, what is happening is we are injecting power back into the network and we're lowering prices. But these two are very similar. Here the power in the loop AMOD system is injecting because it knows it's good for everyone. Here, in the uncoordinated case, the transportation network is injecting power because it sees these prices, it thinks, ka-ching, I'm going to make money, and it injects a lot of power into the network. But it doesn't get those gains, because by injecting power into the network, it lowers the price for everyone, including the price paid back to itself. So yes, we do V2G, and we have a V2G efficiency. I think it's 90% attached to this. So cars can't arbitrage electricity.
In that line where you say expenditure, is it the LMP times the
the load? Correct, yes. Again, I have a similar line. There was some debate now to present these results. We felt that also presenting the cost in addition to the price was a bit confusing, but we're honest, we will come back to this.
I think that's the right number for Texas, because everybody gets paid.
Yeah. Thank you. Any other questions on this from the... Shall we? All right. So these results are nice. How do we realize them in practice? And we have two nice theoretical results that show us how we can use these nice coordinated results when where agents, in particular transportation operator and the power operator, are self-interested. The first result is that the social optimum I showed you is a Nash equilibrium. So if we can get to that optimum somehow, if we can compute this optimum, neither transportation operator nor the power operator is going to be willing to move away from it. It's not only good for society, it's also good for every agent individually. So that's pretty neat. But still, you have to compute this social optimum, and in the optimization problem I showed you before, you need to have access to private information from both the power network operator, namely the cost of electricity that you have to pay out to the generators, and private information for the power network, predicted customer demand, which is not something I think one would be willing to share. So how do we get around this? We're able to extend the result in a paper by Manuel Izadeh, on which I think you believe we're an author, to show that one can use a dual decomposition algorithm to distributely compute this optimum. And the way this dual decomposition algorithm works is the TSO only has to share information that is the transportation operator only has to share information that is going to be public anyway, namely the proposed charging schedule. And the power network operator only has to be shared public information, namely the proposed locational marginal prices. So to recap, the social optimum we saw is an Nash equilibrium, so if we can compute it and get there somehow, neither the TSO nor the power network operator are going to be defecting from it, and we can compute this optimum in a distributed fashion without sharing private information, which tells us that the results we showed are applicable to the case with self-interested agents. Now this is nice, but those simulations take a while to run. They took about 1 hour to run a 3-year-old desktop, which is not terrible, but if we want to control transportation network in real time, we need a much higher tempo. So we designed a real-time power-in-the-loop AMOD algorithm, and we had to overcome 3 obstacles. The first one is computation time. 1 hour to compute a solution is too much. We want to go down to minutes or seconds. To achieve this, we made one additional assumption. We assume that once a vehicle has a customer on board, they will always take the fastest route. This is similar to what we did before for congestion. And it also makes sense from a customer satisfaction perspective. So we don't compute the routes for the customer carrying vehicles. We also assume that these vehicles never charge when they have a customer on board, which again makes sense from a customer satisfaction perspective. Note that we still optimize the initial and final state of charge of the customer carrying vehicles. We get to decide that. Just once they have a customer on board, they go straight to their destination.
By shortest route, you mean shortest time?
Sorry?
Shortest time or shortest distance? So
shortest time, yeah, thank you.
Yeah, you're taking congestion into account.
Yes. Yeah, in the real-time algorithm, what we'll do is we'll reuse the same code from the other simulation and just use Dijkstra, look at the state of the roads, and thank you for catching me on that. So this is in principle suboptimal. It may not return the same results as we had before, but we checked. It turns out that we get very high quality results, and this allows us to get the computation time down from 1 hour to 1 minute on the same 3-year-old desktop computer. The second obstacle we need to overcome is uncertainty. Specifically, we may have very good models for power demand and customer demand, but they're not perfect. So how do we incorporate information as we get it? To do that, we designed a receding horizon implementation where every couple of minutes we solve this optimization problem based on the current state of the system and on future demand and on predicted future demand. We implement the first step of the optimal solution, and then 2 minutes later we circle back, we look at the current state of the system and re-optimize, and so on and so forth. This also allows us to use a shorter optimization horizon. We no longer look at a 10-hour horizon, we look at a 2-hour horizon, and by doing that we get the computation time down to 2 seconds on the same computer. The third obstacle we need to overcome is that the output of the optimization algorithm is fractional, so we can't use it in practice unless we're willing to cut up customers. Which is bad for customer satisfaction. So how do we get around that? We take the fractional output, we sample it, and in this way, for every vehicle and for every customer, we sample a state of charge that we want them to leave at. For every vehicle, we sample an action that we want them to take. And by doing this we get a solution that is feasible for the vehicles and in expectations recovers the optimum. So how well does this work? We have a video to show you. It's a very busy video. So the size of the nodes and the size of the links denotes the number of vehicles on there. The color denotes the state of charge of the vehicles. The triangles going up denote the number of vehicles charging at a node, and the tiny red downward-facing triangles denote the number of vehicles discharging at one node. We compare our algorithm with a greedy algorithm, where again the transportation operator looks at current prices, optimizes its operations, assuming that what it does will not have any impact on the prices. And then, of course, there is an impact, and 2 minutes later, the transportation operator re-optimizes and so on. Our results are a 14% reduction in the electricity expense for the transportation operator compared to the greedy case, which comes out to $60 million a year. The savings for everyone in Texas are in the order of $75 million a year, and specifically, coordination allows us to reduce the price of electricity in Dallas-Fort Worth by just shy of 1%. I don't have a bullet point for that, but the customer travel times are the same. Indeed, the wait time is slightly decreased. We don't know if that's significant, but coordination does not make things worse for the customers. If anything, it makes it better. So this was the last result I want to share with you, and we're ready to conclude. Let's recap what we discussed today. We looked at the interaction between AMOD systems and our cities with specific attention to the interaction between fleets of self-driving cars and congestion, and fleets of electric self-driving cars and the power network. We show that under mild assumptions that are verified for US cities, rebalancing, moving from private cars to AMOD systems will not increase congestion. We designed a real-time algorithm that realizes these gains. We tested it in a case study of New York City, and we showed a 22% reduction in customer wait times compared to a state-of-the-art algorithm. For what concerns the interaction with the power network, we designed a model that captures the interaction between these two systems. We used this model to show that the AMOD systems can greatly help the power network by reducing power prices for everyone and reducing the power bill for whoever is managing the transportation system. We showed that these results do not require the transportation operator and the power operator to cooperate. Indeed, even with selfish agents, we can realize these results. And we came up with a real-time algorithm that allows us to control transportation networks by accounting for the externality that they impose and optimizing the externality they impose on the power network. So where do we go from here? Our lab is looking at many facets of AMOD systems. And first of all, I want to mention some great research being done by Ramon and Matt, who I believe are somewhere here, on predicting customer demand, not only a point prediction, but a distributional prediction of what customer demand will look like, and using this information for stochastic control of AMOD systems, accounting for this uncertainty. Personally, I'm more excited about further exploring the interaction between the AMOD systems in our cities, and I want to focus on understanding how these systems will interact with existing public transportation. Are self-driving cars going to replace buses? Are they going to act as feeders for the buses? How about light rail? How about heavy rail? We think that network flow models can give us both the socially optimal answer to these questions and pricing strategies that will align self-interested customers with these optimal strategies. Also, we think that our models for power in the loop AMOD have a lot of mileage left in them. Specifically, two things we really want to look at are whether we can use this cooperation to foster adoption of renewable energy. Today, adoption of rooftop solar is being hindered by the fact that the power distribution network is not ready to handle power being injected at the leaves. They were not designed to do that. And the question is, can we use this sort of giant battery we can drive around and plug in to increase adoption of rooftop solar? The second interesting question is, what will happen to pollution? Can we use AMOD systems to reduce the use of polluting peaker plants that only get turned on 2-3 times a year? And what is the effect on the life cycle pollution of these AMOD systems? Stay tuned for details. We hope to have results by April, I think. So this concludes the technical part of this talk, but before I can let you go, I want to make some acknowledgments. First of all, thank you very much to the committee for being here. Professor Goldsmith, I'm so honored you're here. Thank you so much. And your work with Manoush on power in the loop, on the interaction between EVs and power network has been a cornerstone that we built our results on. Professor Schwager, Professor Koch-Endorfer, thank you so much for being here. Thank you for your feedback, especially your feedback in the Greenlight meeting. I hope it made this presentation better and it made these results better. Professor Rajagopal, thank you so much for being here. Your work on societal networks, on the interaction between transportation networks, power networks, and data-driven control of these systems is amazing, and I'm really looking forward to our discussion. Mark, you've been an amazing mentor and an amazing advisor. Every time we've met over these 5 years, whether it was in your office, in a hallway, as you were going to grab your motorcycle and was running after you, from every meeting I've learned something. And I think thanks to you, I've become not only a better researcher, but also possibly a better person. So thank you so much for that, possibly, not a good person. So thank you so much for taking a chance on me. Thank you for giving me this opportunity. And yeah, thanks for everything, being an amazing teacher. A big thank you goes to my co-authors, in particular Rick, Ramon, Manoush, and Youssef. It has been a privilege working with each of you. Thank you so much. Also, I spent last summer at JPL. A big thank you goes to everyone I interacted with at JPL, in particular Saptarshi, who was a great mentor, Dr. Mike Wolf, and Dr. Adrian Stoica. I do hope there will be more opportunities to collaborate in our future. On the personal side, there are some acknowledgments I want to make. First of all, the Autonomous Systems Lab. Guys, you're great. I sat in that lab for 5 years. To every present and past member of the lab, I've learned so much from you. It's a privilege sitting in the same room as you. Thank you for our conversations, which have taught me a lot. And thanks for sticking with my rants. I really appreciate that. To the Stanford Astronautical Society, in particular Albert, Ari, and Gong, we've had so much fun under the stars. To Rachel and Steve of Hog Island for teaching me about perseverance and, in a way, about love. On a more serious note, a big thank you goes to my Melin, my friends from away, in particular, but not only, Marzia, Selene, Flavia and Federica. Thank you for sticking with me, despite the distance. Thank you for nurturing our friendships. We only meet a couple times a year, but every time we do, I feel at home. So thank you so much for that. My mom and dad and my little brother, who may or may not be watching, I have a fun story here. I was telling my mom a couple weeks ago, you know, after the defense for the private part, I'm probably going to take the afternoon off, go to Berkeley. And she looked at me and said, why would you do that? Aren't you supposed to be studying? Don't you have work to do? So I'm taking the afternoon off, Mom. But that spirit, this idea of, you know, never giving up, always trying for more, always going in one more round, that's why I'm here. So thank you for that.
Doesn't it depend on whether you pass or not?
It probably does, yeah. If I were not to pass, there would be some significant work, and yeah. I'm hoping to take the afternoon off. Thank you for catching me on that. Thanks. The final and biggest thank you goes to Vale. Vale, you've been at my side throughout these 5 years. You cheered with me when things were going well. You cheered me up when things were not going well. You were my rock. And you gracefully accepted my bigamy every time I was not with you, but with my mistress, research. So all I can say is that I would not be standing here if it's not for you. I just wouldn't be here. So thank you. The final thanks goes to every one of you for coming out on a Thursday morning at 9 a.m. to hear us talk about cars. And now is your time. I'm sure that you have lots of interesting questions about this research, and I'll now be extremely glad to answer them. Thank you. For those of you on the live stream, type in your questions and Andrew will relay them. Please.
So with the flow model that you talked about in the earlier part of the talk, how would you expect that to change if at all, if there were multiple transport operators, so lifted and go both fighting for the same customers?
Thank you. That's a great question. I mean, it goes into the game theoretical side of things. Per se, the network flow model is great when you want to do global optimization. If you want to also account for these game theoretical effects, you do need to use different tools. I think, yeah, the nice thing about linear models, and specifically the network flow models, is that they give you not only an optimal solution, but also shadow prices. And often these shadow prices can be used to align the interests of self-interested actors with the social optimum. Specifically, for what concerns congestion, the way we use the network flow model is just for routing. So if you, in the simulations, as Professor Goldman pointed out, we assume that we have the roads all to ourselves. What if you don't have the roads all to yourself? That's fine. I mean, the MPC algorithm will work anyway, possibly just as well. It doesn't care what the capacities is. They're just numbers to it. For what concerns the interaction with the power network, that's a great question. Do we still get the game theoretical results? That's an active area of research. So I don't have an answer for you, but we're looking into it. Does this answer your question? Thank you. Enzo.
Did I understand correctly that the model of the network, the power network, is a DC network?
So yeah, the question is, did we model the power network as a DC network? Yes, we did.
Okay. Have you even tried to look at what happened with the AC model, which is crazy?
No, we haven't. So keep in mind, here we are looking at the power transmission network, and I'm not a power network expert, but I know one, Manouche specifically, and she tells me that the DC model works quite well for transmission. There is an area of research in our lab, the area of research being Alvaro right there, who has been looking for the last 3 months at more sophisticated models to also capture the distribution network, where really the DC model does not work. And we hope to have results on that, well, not by RSS, maybe by March. So it's an active area of research, but I don't have a simulation to show you with the AC model. I don't believe that as far as transmission is concerned, it would change much, but I may be wrong.
I expect it to work much, much worse.
You think so?
Yeah.
Why?
Because you have to solve an anti-hard problem every time you plug into something.
Oh, you mean for synthesis?
It's from computational standpoint.
Oh, from synthesis. No, you wouldn't want to use that for synthesis. I misunderstood your question. So, no, I think that the DC model is perfect for controlled synthesis. What you can do is you can then simulate this with a more sophisticated AC model and see how far off you were. You wouldn't want to use an AC model for synthesis. Yeah, it's again, it goes back to the fact that for many of these effects, there are very sophisticated models out there, very good simulators. You can't use them for synthesis in your lifetime. So we did have to dial down and try try to hit this trade-off between being expressive enough that we capture the effects we care about and simple enough that we can solve these things. Also, to go back to further add to this, it's not only about how long it takes to solve a problem, it's how long it takes to reliably solve a problem. So I'm a controls person, we want to run these things in real time. Maybe you can just stick the AC problem in fmin con and many times you'll get lucky. But the really nice thing about linear programs is that you roughly know how long it's going to take. It takes 20 to 40 iterations of interior point, and you know exactly how much one iteration takes, which gives you peace of mind when you're deploying this in real life because you can't afford to have the optimizer say solution not found. Does this address your question? Thank you. Ben?
So one of the most expensive parts of the car, of electric car, is the battery, and presumably this is a design decision of an AIM fleet designer. And for cities, they may in fact just dial back the battery capacity because the average trip time is much shorter than a Model S has to have, for example. So how sensitive are your results to the possibility that all your cars have very low capacity compared to the, let's say, mean energy expenditure?
That's a great question. So the simulations that we ran used one battery capacity. Specifically, we took the spec sheet from the Chevy Bolt, which is one of the best self-driving cars you can, EVs you can buy right now. Self-driving cars next year, no, 2019. We have looked at that. We did look at that in a 2016 paper for ICRA, where Rick Zhang was the lead author. I expect there to be a trade-off for a given level of customer satisfaction. I expect there to be a trade-off between fleet size and battery capacity. Intuitively, if you have a smaller battery capacity, you're going to have to be charging more. From a design standpoint, I think you really want a battery that can last you through either the morning commute or the afternoon commute. Because I suspect, but it is a hunch, that the operations will look like charge until 5 a.m., then ride out the morning commute, charge around noon, and then ride out the evening commute. Which is also nice because it means that the charging profile is not aligned with the ducky profile of demand in the power network. So, but I don't have a plot on this. I think we had some results for ICRA where we looked at that, and it's really a trade-off between battery size and fleet size because you need a certain amount of energy to satisfy trips. So if you have less of that, you need more cars because you can't charge them in time to get them back. Does this address your question? Questions? No? Yes, Stefan and then Ed.
How hard is it to incorporate heterogeneous cars into your models?
That's a very good question. You'd probably want to have two networks with some, I'm just thinking out loud here. There are two aspects here. One is, can we look at carpooling? Can we fit multiple vehicles in a car? That's hard with the network flow model. It can be done, but it requires you to keep track of every individual vehicle, and that's not something you want to do for scalability reasons. Could you have different types of cars with different battery sizes? My hunch is that that would not be too hard. You just have one network for every car, and then you distribute customers, and writing the constraint that says the customer has to be picked up by one of these is not hard. I mean, it breaks total modularity, but that's already long lost in the power in the loop AMOD model. I'm just thinking out loud here. I can get back to you. I have to sit down for an afternoon and run the numbers, but I think it will be doable. I'll take Ed's question first.
So you mentioned that you don't really consider exogenous congestion in the case of the New York City model. You just
in the simulations, yeah.
You decrease the road capacity. I was curious, when I think about congestion in my regular life, I think one of it is just a lot of cars on the road at this point, but another time congestion occurs is when this particular two-car accident occurs and this road becomes shut down for a while. I guess would you just say that this is a 1 hour event, so that's time invariant, quote unquote, again, and you just put that, you solve your model with that as a constant, like that road capacity?
Thank you. Yeah, I mean, you solve your model every 5 minutes. So for the times you solve the model within that hour, yes, you would do that. And I think we had a question the day before yesterday at the rehearsal, you weren't there, that was on the similar line. What happens if a road is shut down? the theoretical result requires node symmetry, and you can't get around that. What happens if node symmetry is violated? We have some simulation results from New York City where we tried reducing the cut symmetry by a lot. And turns out that the fact that rebalancing vehicles do not increase congestion is quite robust to highly non-node symmetric roads. In practice, the algorithm doesn't care. It's just that the capacity of the road goes down to 0, so you will route away from it. And the worst that could happen is, in order to get a feasible solution, you would drop a few more rebalancing trips. But it can accommodate that. Does it address your question?
Yeah.
Also, I should be repeating questions when they're asked. Remind me. Yes?
My question is, what do you think it would happen if some of the cars, instead of being fully electric, would be hybrid electric in the power mode framework?
That's a great question. Part of it goes back to heterogeneity. I'm wondering if all of it goes back to heterogeneity, because now you'd have to optimize also there is an extra trade-off. It's a more complex problem where you also want to decide, are we talking about plug-in hybrids or something like the BMW like range extender, or plug-in hybrids? To me, it goes back to heterogeneity. The question is, would a network flow model be able to capture that? Probably. We have to sit down and run the numbers. My feeling is that, yeah, you have a battery capacity, and when the battery is depleted, you could have self-arcs where you could have actually, for every road network, you have a road link where with 2 arcs, one arc where your battery charge depletes, and 1 arc where it doesn't deplete because you're using your gas-powered engine, but you have a cost that accounts for that. It's very hard to come up with a network flow model in 30 seconds, but that's where I would start from. Does it address your question? It doesn't, but does to satisfy you and we can sit down, not this afternoon, but tomorrow, and maybe this afternoon, and figure it out.
But the morning is still long.
Sorry?
The morning is still long.
Yeah.
Afternoon kicks in.
But I assume that you guys would want me. Well, we could sit down here and try to figure it out.
2 hours.
No? Oh, okay. Ed.
So a mathematical consequence of modeling things as a network flow and in general solving it as an LP, or in general like a convex problem, that the solution is going to be unique, or the outcome is going to be unique.
Yes.
And having not thought about the problem at all, I guess this is maybe a little bit surprising, because when I think about ways that I could route huge networks of cars, I might think maybe there's method A and method B, and both of these sort of.
The optimum is not unique. The cost is unique.
Surprising that it's not multimodal.
The question is, LPs give you a unique solution. Is that surprising? Are they multimodal solutions? I don't think that you get a unique solution. You get one optimal cost, but it may lie on a facet of your polytope. Will that facet be big enough or jagged enough that you can get multimodal behavior? Maybe. That is my answer. I think, I would be surprised if there was, if it was always, a single unimodal solution. But for instance, when you have a ton of charge of generators that all have the same price because they're all natural gas powered, you can get the same cost with very different assignments in the power network, and they'll all be optimal. So I think that's where multimodality comes in, and I could check that, but I think the interior point is that it's hard to nudge them. I could try with the simplex, having it start from different, but simplex is super slow on these problems. I could run the numbers and get back, or I'll discuss that with you, and so you are on the spot because you're the expert. But that is my answer. Does this address or start to address your question?
Yeah, it's more a question of intuition. Like, if you're not surprised, then
No, I would be surprised if it was unimodal, but I don't think it's unimodal. I think the cost is unimodal, which is...
I definitely, did not do that. Questions?
Anything from the live stream? No? I did tell them when I was talking told them to ask questions, and Andrew would ask them, but clearly, no. We may have some folks from JPL watching. That's why
Okay. I guess we'll take.
Thank you, guys. Thanks for being here.
We'll take a 5-8 minute break and then.
Oh, I didn't start that. Thank you. Well, we haven't discussed yet, so thank you.
Good, like,
No, it's nicely done. Really clear.